Hello everyone. Good time. Instead of say good morning or good afternoon or good evening, it's better to say good night, good time. Now we are starting the English part of the third day of the seminar. Just remind you, after the last lecture, again, we will take another group photo. Now I'm asking Professor Abdullahi to introduce the first two speakers of this session. Professor Abdullahi, please.
Hello,
I can't hear you.
Hello. Can you hear me? Hello. Hello. Yes. Hello, everyone. Welcome to the third session of the seminar. It's my pleasure to introduce Professor Mohammad Moslehian. He is Professor of Mathematics and also General Director of Research at Ferdowsi University of Mashhad. He received his PhD and Master of Science from Ferdowsi University of Mashhad. He also is a Senior Associate of ICTP and a member of Mathematics Division of the Academy of Science of Iran. He was a member of Executive Committee of Iranian Mathematical Society, Editor-in-Chief of the Bulletin of Iranian Mathematical Society. He also was a gold medal winner of the 13th Annual Iranian University Student Competition in Mathematics. He is founder of TUSIMAT Research Group and Functional Analysis Award, which partially supported by Duke University Press. His research concerns functional analysis, CSR algebras, Banach spaces, Hilbert C modules, operator theory, and linear algebra, matrix analysis, operator and norm inequality. His talk is about, his talk title is Chow Davis-Jensen Inequality Revisited. Thank you very much, Professor Moslehian. Please share. Please start your talk. Thank you.
Thank you very much, the Chairman, Professor Abdullahi, and the organizing committee of this successful seminar. My talk is about the Choi-Davis-Jensen inequality. First, I would like to fix our notation. Let B of H denote the algebra of all bundle linear operators on a complex Hilbert space H with the identity I and equipped with the operator norm defined by the supremum of the norm of AX over all unit vectors X. The adjoint A star of A is uniquely defined by this equality. By a C-star algebra, we mean a norm closed star subalgebra of BH for some H. Algebra BH can be identified with the matrix algebra Mn when dimension of H is n. In this talk, a capital letter displays an operator in BH. In addition, we assume all real and complex valued functions are continuous. An operator A is called self-adjoint if A star is equal to A. equivalently, A is self-adjoint if and only if the inner product of AX and X is real for all X in H. An operator A is called positive if the inner product of AX and X is non-negative for all X. Then we write A greater than 0. If A is invertible and positive, then we write A greater than 0 and say that A is strictly positive. For self-adjoint operators A and B, we say that A is below B if B minus A is a positive operator. The partial order is called the Loner order. A mapping phi from BH to BK is called positive or strictly positive whenever it takes positive or strictly positive, respectively, operators to positive operators. It is called unital when phi of I is equal to I. This means that phi preserves the identity operator. If BK is replaced by the field of complex numbers, then we call phi a positive linear function. In the case that the norm of phi is 1, then we say phi is a state. Okay, when H is a Cn with the following usual inner product, the algebra BH can be identified with the matrix algebra Mn. If A is in Mn, this means that A is a matrix, then we can consider A as the linear map from Cn into Cn, taking each column matrix X to the column matrix A multiplied by X. In this case, the adjoint of our matrix is indeed the conjugate transpose. And the spectrum of A is the set of all eigenvalues of A. In this talk, a capital letter displays an operator or matrix. In addition, we assume that all real and complex valued functions are continuous. An operator A is called normal when A commutes with its adjoint. A typical example is any matrix A for which A star is equal to PA for some polynomial P. It is self-adjoint when A is equal to A star, or equivalently, the inner product of AX and X is a real number for each X in H. A typical example is this matrix, in which A and C are real numbers. An operator A is called positive when this inner product is non-negative for every X in H, or equivalently when A is self-adjoint and its spectrum is contained in the positive half of the real line. And we write A greater than 0 to indicate that A is positive. A typical example is this matrix in which A and C are non-negative numbers and the determinant of this matrix is non-negative. If A is invertible and positive, then we say that A is strictly positive. If A is a positive operator, then there is a unique positive operator B such that A is equal to B squared. B is called the positive square root of A and denoted by A to the power half. In particular, the positive square root of A star A is denoted by this, and it's called the absolute value of the modulus. For a function f defined on the spectrum of A, the operator fa is defined by the functional calculus. In particular, when f is a polynomial, then f of A can be obtained by replacing t formally by A. For self-adjoint operators A and B, we say that A is below B if B minus A is non-negative, is a positive operator. This partial order is called the Loner order. Okay? A map phi from BH to BK is called positive when it takes positive operators to positive ones. For example, trace of A is a positive linear functional on the matrix algebra Mn. Phi of A, defined by C star AC, in which C is a fixed operator, is a positive linear functional. When A is positive, we see that phi of A is also positive. If we define phi of A to be the inner product of AX and X for a fixed unit vector X, then this phi is in fact a state. By a state, we mean a positive linear functional of norm 1. The fourth example is the expectation. The expectation is defined by this integral on the Hilbert space L2 on a probability space omega and mu. In the classical probability theory, the variance of a real random variable x is defined by this. Variance of x is expectation of x2 minus the expectation of x to the power 2. One of the basic properties of this quantity is its positivity. As a non-commutative extension of this notion, we can define variance of an operator A to be phi of A2 minus phi of A2. Here, phi is a positive linear mapping. This is called the variance of A with respect to phi. An interesting question is this: does phi of A squared is below of phi of A squared? We know that when we have we are dealing with convex function T2, then we know it is true. This is called, in fact, the Cadison inequality. If we replace T2 by a real convex function f, then we write f expectation of x is less than or equal expectation of f of x. This is now the difference of these quantities is known in probability theory as Jensen gap. Another nice question is this: if we replace expectation by a positive linear mapping, is the obtained inequality valid for any convex function f? So here we have two interesting questions. My talk is about answering to these questions. The first question. The Cauchy-Schwarz inequality states that the left side is less than or equal the right side for all complex number aj and bj. The Cauchy-Schwarz inequality for positive functionals on BH says that if phi is a positive linear functional on BH, then we have this. You can see similarity between these two formulas. If we replace B by the identity operator and replace A by its adjoint, we arrive at this inequality. Phi of A squared is less than or equal phi of A squared. Our question here asks us what happens if we replace the complex numbers C here by the algebra of Bk for a Hilbert space K. In fact, if we have a unital positive linear map phi from BH to BK, Caddison proved that if A is self-adjoint, then this inequality holds. Choi proved that if A is normal, then we have this inequality, and you can see this inequality is in fact a generalization of Caddison inequality. Sharma and his collaborators gave a generalization of the Caddison inequality by showing that this matrix of operators is positive. Now we try to answer to the second question. It is known that a function f defined on an interval j of the real line is convex if and only if this inequality, which is called the discrete Jensen inequality, holds, in which a1 up to an are in J and t1 up to tn are positive real numbers with whose sum is 1. The continuous version of the Jensen inequality is of this form. Here we have a convex function f, and h is into absolutely integrable functions on a probability space omega nu. Brown and Kiyosaki proved that if f is convex on the interval 0 infinity, such that f of 0 is 0, then for each vector x in the closed unit ball of H, and for each positive operator A, we have this inequality. Here, C is a contraction. By a contraction, we mean an operator C such that its norm is not greater than 1. The simplest operator version of the Jensen inequality is of this form. Here, phi is a state on BH, f is a convex function on an interval J, and A is a self-adjoint operator with a spectrum in J. In particular, if we consider the vector state phi defined by this inner product, here again x is fixed, is a unit vector, then the Jensen inequality above here can be written in this form. F of the inner product of ax and x is less than or equal the inner product of fa, x, and x. For example, if we take H to be the finite dimensional Hilbert space Cn and A to be the diagonal matrix with diagonal entities square root of T1 up to square root of Tn, whose sum is again 1, and we assume that x is a column vector a1 up to an, then we arrived at the classical discrete Jensen inequality. So this is, such a star is in fact a generalization of the Jensen inequality. What happens if we replace phi by a positive linear function? It is known that the inequality does not satisfy and does not hold, and so we should find some conditions in such a way that we get a true inequality. To achieve an operator version of the Jensen inequality, we need a definition. This definition is a generalization of the notion of convexity. A real valued function f defined on an interval J of R is called operator convex if we have this inequality for all self-adjoint operators A and B with spectra in J and all T in the interval 0 and 1. If minus f is operator convex, then we say f is operator concave. For example, T2 is operator convex. Of course, every operator convex is automatically convex in the classical sense. But the converse is not true. For example, the exponential function et is convex, but not operator convex. If f is an operator convex function on an interval J, then Choi-Davis-Jensen inequality states that this inequality holds, in which f is an operator convex, phi is a unital positive linear map, and A is a self-adjoint operator with a spectrum in J. the operator convexity is equivalent to the Choi-Davis inequality. The fact is due to Hansen and Peterson. Why we call this inequality Choi-Davis-Jensen? Okay, Jensen inequality is related to the classical Jensen inequality. Davis proved this inequality when f is operator convex and phi is a unital, completely positive unital linear map. By completely positive, we mean that all maps phi n from mn of bh to mn of bk are positive for all n. Choi showed that the Choi-Davis-Jensen inequality remains true for all positive unital linear maps phi and all operator convex functions f. Dr. Mariam Khosravi and her collaborators extended the Choi-Davis-Jensen inequality as the following form. Let phi 1 up to phi n be a strictly positive linear maps. Recall that a strictly positive linear map is a map which takes strictly positive operators to strictly positive operators. I mean, when A is positive and invertible, then phi of A is also positive and invertible. And let phi is their sum. Then we have this inequality, and you can see here we have a term middle between f of phi of A and phi of f of A. And we showed in our paper that these inequalities are really strict, can be strict. So this is really an extension of Choi-Davis-Jensen inequality. An extension of our theorem is given by Beck-John for measurable operators in semi-von Neumann algebras and for convex functions. If f is convex but not operator convex, Bhatia and Sharma in 2012 showed that the Choi-Davis-Jensen inequality remains true for every 2 by 2 Hermitian matrix A. A version of Choi-Davis-Jensen inequality for a spectral periorder instead of the loner order in the setting of von Neumann algebras is given by Antezana and his collaborators. Burin and Lee gave a variety of Choi-Davis-Jensen type inequalities for general convex and concave functions. And Niezgoda employed generalized inverse of some linear operators and presented a refinement of Choi-Davis-Jensen inequality. In fact, Niezgoda also extended our work with Dr. Khosravi. The classical Chebyshev inequality asserts that if AI and BI, I between 1 and k, are increasing sequences of positive real numbers, then this inequality holds. If one of sequence is decreasing, then the reverse inequality holds. Chebyshev inequality is in fact a reverse of the gross inequality, and several operator versions of reverse Chebyshev inequality, named as the gross inequality, was established in a paper by Motaro and his collaborator. Burin and Ricard presented an asymmetric Cadison inequality by showing that if gamma is between 0 and 1, then for every positive operator x, we have this inequality. This inequality implies a non-commutative version of Chebyshev inequality of this form here, in which alpha is between 0 and beta. A generalized version of the non-commutative Chebyshev inequality was presented by Fruta of this form under some complicated conditions. A natural question is, what are operator versions of Chebyshev inequality with two operators? Please have a look here. Here we are dealing with an operator x, while in the Chebyshev inequality we have two sequences, ai, bi. So we would like to have an inequality including two operators a and b. Okay? One version we may guess is suitable is this inequality 1, but unfortunately this inequality does not hold in general. To show this, assume that phi is the unital positive linear map defined by this: the compression of a 3 by 3 matrix to the 2 by 2 matrix in the left up corner of the matrix. And consider these positive matrices. Then we can see that the left side is not less than or equal the right side. This means that the difference of these operators is not a positive operator. Another possible extension is this inequality. So we have Chebyshev inequality, the numerical version of Chebyshev inequality in our mind, and we are seeking to find some operator versions of this inequality. Again, this is not true in general. Again, if we use the same positive linear map phi and positive operators a and b as above, we get phi a, phi b, phi a is not below of phi of a, b, x. Burin and Ricard presented a variant of 2 in the setting of complex matrices Mn. So they consider matrices instead of operators, and show that we have this inequality in which V is a unitary matrix. By a unitary matrix, we mean a matrix such that V star V and VV star are equal to the identity operator. We note that a weaker version of 2 is this, and this is valid for all positive operators A and B. The first result of Kuhn, Speaker, and Nakamoto extended the works of Burin, Ricard, and Furuta. It reads as follows. Here you can see we have a unit-hall positive linear map phi, and f and g are operator convex functions. Then for every positive invertible operator A, there exists a partial isometry V such that this inequality holds, provided that this function isometry V such that this inequality holds, provided that this function is also operator concave. As a consequence of our central result, we have this inequality. This inequality says that if phi is a unit-hall positive linear map and R is between 0 and half, and F is an operator convex function, then for every strictly positive operator A, we have this inequality. The next result gives a CDG type asymmetric inequality. Asymmetric inequality says that if we have a positive operator X, a positive linear map phi, then we have this inequality. Another generalization is given here. Okay. Another consequence of our result is this. Assume that f is a function. If f2 is operator concave, then we have this inequality and this inequality for every unit-hall positive linear map phi and positive invertible operator A. Okay. Particularly, we have this inequality. The first inequality says that the absolute value of phi of A to the power gamma phi of A is less than or equal phi of A to the power gamma plus 1. And the other is this. Here, again, phi is a positive linear map. A is a positive invertible operator or a strictly positive operator, and gamma is between 0 and half. These results, in fact, extend the results of Burin and Lee and also Furuta, as I showed them in my previous slides. The next theorem presents a reverse of this inequality. To get a reverse of an inequality, usually we have to consider our operators are bounded above by a constant and bounded below by another constant. In the sense that we assume usually A is between Mi and Mi. This is not a serious assumption, since any positive operator is bounded from above by its norm. But the left inequality is important. If A is greater than M for a strictly positive number M, then A is in fact an invertible operator, and this is an equivalence between invertibility of a positive operator, and we have an inequality of the form of M less than, strictly less than A. Okay, let phi be a unital positive linear map. Let f be a function from the interval of m and m to the positive half of the real line, 0 and infinity, such that f2 is strictly concave. If A is a positive operator, then we have this inequality. Here, chi is a constant, can be computed in this form, and one can show that this constant is sharp, in fact. Okay. When f is the power function, the previous result, this theorem, turns to the following corollary, and in fact, it provides a counterpart to the symmetric Cartesian inequality of Burin and Lord. It says that if phi is a unital positive linear map and gamma is between 0 and 1, if A is a positive operator, such that A is between M and M. Here again, the lowercase m should be strictly positive. This means that A is strictly positive or invertible. So we can get this inequality, and we can simplify this inequality of this form when alpha is between 0 and beta. Finally, in a particular case, we have this inequality. This inequality says that if phi is a unital positive linear map for every positive invertible operator x and gamma between half and 1, then we have this inequality. Okay, my talk is over, and thank you very much for your attention. Professor Abdullah, Rashid, can you hear me?
Very much. Thank you very much, Professor Salim Moslehian. Any question? Any question?
Okay.
There is no question.
Okay, there is one question by Professor Zhu. Can you state some applications of these inequalities?
Yes.
Please, Professor Al-Musliyan.
Yes, Professor. Yes. In general, the operator inequalities can be used for operators acting on Hilbert infinite dimensional Hilbert spaces. For example, we may consider operators in B of L2. L2 is squarely summable sequences, okay? And this is also, in fact, a generalized version of matrices or sequences, finite sequences. So our operators, in fact, our inequalities are generalization of several inequalities in the matrix theory. So you can see in matrix theory all inequalities, for example, Choi-Davis-Jensen inequality or Jensen inequality, are many applications in statistics and so on. For example, you see Jensen inequality and also other inequalities, Gauss inequality, Chebyshev inequality, have several applications in statistics, economics, and also quantum physics. In particular, inequalities on operators are useful in quantum information theory. For example, one of my postdoc researcher, Professor Dr. Dadha, we get some inequalities in this area which have some counterpart in the information theory, quantum information theory. So this is a general question. What's the applications? Okay, the application can be found. Maybe some of them are now very pure, but we hope they find some application in the future. Dr. Abdullah?
Thank you very much for your nice talk. Thank you. We have time for next talk.
Thank you very much.